we'll be discussing exponents and logs, exponential and logarithms function. These logs and exponential functions, our interest is to study the investment and the growth of population. So we find them more relevant in terms of giving us an indication of growth of our investment and also growth of our population. So logs and exponential functions are more relevant in terms of studying the behavior of our population and the behavior of our investment. So today's class, it's about these two concepts, which is exponential functions and logarithms function. Like I said, topic of the day is exponential and logarithmic function. Like I said, if you want to study the growth of your investment and population, exponential and logarithm functions under nonlinear functions. These are two relevant functions that can help you to study properly your population and your investment. So under this logarithm and exponential, where our interest is to study the growth, can be investment or population, we have three ways, three main types of growth. Like I said, exponential and logarithm functions, we use them to study the growth. It can be the growth of investment or the growth of population. So we are saying this growth that you are referring to, we have three types of this growth that we are referring to. Functions. We say that unlimited. Two, we have the limited one. Limited growth. And lastly, we have the logistic growth. Remember, this type of growth, they fall under our exponential function. Okay. So let's look at the first one, where our interest is to see if we are interested to study the unlimited growth. And we are saying unlimited one unlimited growth we can use unlimited growth in case whereby we want to study population. How is our population grow? How is our population growing? And also, if you invest your money, investment, so you can apply your unlimited growth to see how the population, maybe population of South Africa is growing from the day to day, and we can also estimate the future of our growth, how it's growing, and also we can do the same thing when it comes to our investment. So it means unlimited growth is relevant where you want to study population and your investment. And in that, for us to model the unlimited growth, we are given a function where is f, in brackets t close brackets, equals to a e to the power rt, whereby we say t in this case represent time, and or while our a and r, they are our constant. This is our constant. Looking at this formula. So, like I said, this formula, you can use it if you're interested to study your population or your investment. If you want to see how these two are growing, so you can use unlimited growth. Remember, this is still under your exponential function and logarithm function. So where I said t in this case, or in this function, stands for time, represent time, and we have a and r, which is our constant. So we're going to take this function and take an example to study our population. How is our population growing, or how is the population going to grow if we apply unlimited growth? And if you look at the example that is given to us, it says the population of a village was 753 in 1980. It is given that the population grows according to the function. So we're given a function there where our function is pop. So pop meaning population, pop open brackets t equals to 753 to the power 0.03 times t. Okay, I'll try to explain again this function. This is a given function. And if you remember, we are saying from this function, t represent time. And we have a there, a and r, which is a and r, which is our constant. Then 53 and this case is equals to 0.03. So that is our R. Okay. From there, what we want to see, how is our population is going to grow. And the question further says, okay, if we have to study the population in the current year, so we know that in that case, it's times 0. So if we substitute our 0 there, so it means the population is going to remain the same. But if now we have to study our population after a period of 10 years. We say we want to see, because of the population that we have right now, which is 753, is a population of 1980. So it means in 1980, our population there, it was 753. So now we are saying, okay, let's see if we study our population after a period of 10 years. Now we look at the population after 1990. So we are moving from 1980 to 1990, which is 10 years after. So you want to see after 10 years, how much is our population is going to grow after a period of 10 years. So in that case, we say, okay, now we know what is our T in this case. So our T, we are saying we are studying our population after a period of 10 years. So it means our T in that case is going to be 10 years. So we say, okay, let's see after 10 years, how much will the population grow? So we say, okay, P, pop, open brackets 10, equals to 753 e to the power 0.03. So we have T, if you remember, according to our formula. So we say times 10, which is 10 years of 1990. We are moving from 1980 to 1990. Then what do we do now? We try to simplify what we have. Then 753 remains the same to the power e. Then we multiply what we have up there. 0.03 times 10 gives you 0. Okay. So we need to simplify that. And when you simplify that using your calculator, if you press your calculator, you'll say 753 shift in to the power 0.3, then we get our answer. So it means after 10 years, we'll be having a population of 1,016 and 60. So, after 10 years, we're having a population of 1,016 from 753. That was the population in 1980. Then in 1990, we know that pop, you can say pop maybe, in 1990. So we know that population in 1990 will be having 1,016. So that's after 10 years. So here's another question. We say, okay, let's see if how our population is going to grow after a period of maybe 30 years. So now we're interested to see the growth of population the growth of population in 30 years. We know that in this case, our T is equals to 30, and our A there still the same, 753, and our R still 0.03. So it means this information that we have, we'll just have to put it in our function, where we said our function is pop open brackets T equals to 753 to the power e to the power RT. This is our function. Then all you need to do now, maybe just to substitute what we have. Already I've substituted our A there in that case where we have 753 e to the power 0.03 times 30 years. Then we simplify what we have. So we can start with what we have as an exponent there. We have 7 538 to the power. When you multiply 0.03 times 30, we ended up having 0.9 there. Then we say 753 shift e to the power 0.9. Now population after 30 years, it will be 8,000, rather 1,850.52. So that is our population. So it means in the case of investment, we can also apply the same. The procedure is going to be the same given the investment and how long are we investing. So we can do exactly the same to see how is going to be our growth of investment, the same as we did when it comes to population to see, okay, if we're given this function of maybe f at x equals to a e to the power a times e to the power rt, where we have to study our population. Simple, straightforward. This is what we apply so we can be able to see in future. We can also predict in future looking at this formula. Okay, in 10 years, if everything goes well, no any maybe geopolitical eruption or any catastrophe that will take place. So applying this formula can give you what is going to happen in the future. So the same as we applied here, we know maybe there might be other causes, disease and any fights and everything. But now if everything went well based on the population that we have, it means if we have a population of this, of 3 in 1980, and we have to study 10 years, 30 years to come, then we know that if we are studying it for 30 years to come, after 30 years from 1980, if the population of that village, of that township is 750, we know that if you have to study for 30 years, you know that the population, it will be 1,852, which is top 20, 2010. Okay, let's move. So this is the case if we want to see a population. And also, based on our A, if we have to graph it, this is how it's going to look like. Then we have pop here, and we'll have our T that represent time. And we'll have 1,000 here. And we'll have 2,000. We'll have 3,000, 4,000. Okay, 5,000. Okay. Then here we can say we have, sorry about that. Here maybe it can be our 750 or 753. So remember, we're studying growth, so you know that. And this one is unlimited. So it can just go up unlimited to unlimited. So this is how our graph looks like of our unlimited growth population, where the function is pop, open brackets, t, close brackets equals to 753 e to the power 0.3 t. So this is how it looks like. So remember, we are trying to measure population growth. So let's say there's a case whereby now, okay, our interest is to know that, okay, we want to know, okay, how long is going to take us? Once we talk about is to get the population, to have a population of 3,500. How long is going to take us? The question is, what is going to be our T? Because most of the time we've been given T. If you remember the two examples, we're given T, that the T is 10 years, the T is 30 years. But in this case, we're not given the T, we're given the population. So we know our population is 3,500. We want to know now, having a population of 753. From this, how long is going to take us from 753 have a population of 3,500? So it means our interest is to find t, time. T, remember, represent time. And we are saying our interest is to know how long it's going to take us to have this population of 3,500. Where currently we have a population of 753. Okay. So for us to do that, we say, okay, P pop, pop, open brackets, T equals to 3,500. So this is equals to that. Where you remember our formula is pop, open brackets, T equals to uh, A to the power RT. And we are saying this is given to us. And remember, we are still referring to the old function where we know the population is 750, 753. So, but we are saying pop is equals to 3,000, 3,500. And if our pop is equals to 3,500, it means where we see pop t, we can now put 3,500 equals to, we have our a. Remember, our a is still the same, which is 753 e to the power 0.03t. Remember, our interest is to know the time for us to have, to accumulate this population of 3,500. So what do we do now? We say, okay, let's divide both sides by 753. And when we do that, I'll just swap our function, but still the same. We say 753 e to the power 0.03t divide by 753 equals to 3,500 divided by 753. Then that goes, and we ended up having e to the power 0.03 t equals to, in that case, we say 3,500 divided by 753. Then we ended up having 4.65. So our interest, remember, is to have the value of t. So we apply in, and when you do that, we say in, open brackets, e to the power 0.03t close brackets equals to, in that side, 4.65. 4.65. So when you apply that, we ended up having 0.33t equals to, in there's 4.65. Okay. We ended up having 1.54. Both sides. Then what do we do? This will go and that will go. And we have t, which is t, it will be equals to 1.54 divided by 0.0 to 1.3. So it means this is our T, which is time. And meaning we'll have a population of 3,500 after 51 years. After 51 years and 4 months. This is our time T. And this is what we call unlimited growth. This is unlimited growth. Then we have logistic. We have logistic growth. Logistic growth. So unlimited growth is just grow. So when it comes to logistic, it will grow, but there is a limit somewhere. So it will grow, but there is a limit somewhere. It's not like your unlimited growth where there's no limit. Just continue growing, going up. But this one, there is a limit somewhere. For an example, we can look at an example of maybe a rabbit. A rabbit, let's say there are rabbits that live in. So the more they eat, the more they produce rabbits. They will produce, but there's a point whereby now there's no food. And if there's no food, it means there's no way there'll be further growth. That is why we are saying there's a limit. This one, logistic, it has a limited growth. It will grow, but somewhere it will stop, and that will be determined by, for an example that I made, if this rabbit finished the food. So that tells you that there will be no further growth for a for the rabbits. So that's how is your logistic growth as compared to your unlimited growth, where there's no limit. Like I said, it just keep on growth, like your population, your investment. Yes. So when it comes to your logistic growth, we also given a function that we can use to study this logistic growth. And the logistic growth function is f at t equals to the power negative c times t, where we still know that t, it's time. Then we'll have our constant there, which is a, b, and c. Is our constant. So logistic growth can be used, like I said, to study your growth of pandemics and sales, maybe sales of cars and other variables. But what is important now, let's look at whereby now this logistic growth it used to study a variable where the function is f at t equals to 800 divided by 1 plus 799 e to the power negative 0.1 t. So our interest is to see how many chicken will be infected with the virus given time. So we are saying, okay, at time 0, we find that we want to see at time 0 how many chickens will be infected with this virus. So we are saying, in the case whereby t is equals to 0, we have 800 to power a, where we have negative 0.1 times 0. So we'll have 800 there. We have 1 plus 799 e to the power 0. So we say e to the power 0 is 1 there. So if it's 1, okay, it's 800. 1 plus 799. This is 1. When you multiply, it remains the same. Then we ended up having 800 divided by 1 plus 799. So we ended up having 800 divided by 800. And then we have 1. So this is simply saying at time 0, we'll be having 1 chicken which is infected by the virus. That's what that's what we discovered, that we only have 1 chicken at time 0 that was infected by the virus. So you want to see, okay, after 2 weeks, how many chickens will be, if we leave that chicken with the other group of chickens, now the interest, we are just going to change the value of t. So we say f, now the t is equals to 14. So where we see t, put 14. 14 equals to 800 divided by 1 plus 799 e times to the power negative 0.1 times 14. Then we have 800 divided by 1 plus 799 e to the power negative 0.1 times 14. Then we have 1.1 negative 1.1. Okay, so let's simplify this. We have 800 divided there. You say 1 plus 799 e to the power, what am I doing? 1 plus 799 e to the power negative 1.4. Let's see. We have, let's say 1 plus to the power 1. negative 1.4. Okay, times 799. We have 0.1 times 14 close bracket. Then we have 0.2, let's say 25 close brackets. Then we say 7.99799 times 0.25 close brackets. I got 800, 1 plus 199.75. Plus 1, we have 800 divided. When you say 800 divided by 2.75, then we have 4, or we have 3.99. So in this case, we can just 4. Let's just put it as 4. So by then 4 chicken infected after 14 days. Okay. So we say, what about what T is equals to 100? In the case whereby now T is 100, we do the same as F open brackets 100 close brackets equals to 800. Then we have 1 plus 799 e to the power negative 0.1 times 100. Then we simplify it also. 800, we have 1 plus 7, 9 in brackets. We say e to the power negative 0.1 times 100, close brackets. Then you ended up having 0.00004. Yeah, is it 4.5? Let's say 4. Yeah, 4.5. It's fine. Then now we can say 799 times then 800 divided by 1 plus 0.00004. three, 4. Let's say 3, 4. Okay. Then when 800 divided by 1.004, then we say 800 divided by 1.04. At 769. I don't know, maybe there's something with the rounding there. We get 769. But let's look at our rounding properly, where we say, let's draw a line here. Let's see if we take it the way it is. We say 800 divide by 1 plus 799. To the power e to the power negative 0.1 times 100. What are we going to get? But I prefer to do it step by step so you can be able to see how it goes. 800 divide 800 divided by 1 plus 799 power e negative 0.1 times 100. Okay. If you do it whereby you punch it as it is from the calculator, you ended up getting your 772. So it means here something went wrong when it comes to rounding. Maybe I was supposed to take all the numbers the way they appear in my calculator. So if you find yourself in a case whereby you have a number of zeros, it's better you take it the way it is. Don't maybe round it, just take it the way it is, all the numbers. Probably to be able to give you the same answer, because now I didn't want to punch it as it is in my calculator. But now when you punch it as it is, you take it and you put it in a scientific calculator where it is, you ended up getting this 772. But where I was doing using where now I decided to calculate uh, only this part, just to show you the step by step. It looks like I was supposed to take the whole numbers, whereby in that case, the whole number that I'm referring to, this is the number, negative 0.1 times 100. Yes. So it means I was supposed to multiply the 799 by 0 by 0.000012345453999. Let's see what we get. This is what you get plus 1. Is 800 divided by answer. Yes, it means we are not supposed to round it up to 1, 2, 3, 4, 5, 6, 7 numbers after comma. We're supposed to take the numbers the way they are. So now we can be able to get the correct value. Whereby now we have the correct value here. It means supposed to be 0, 3, 6, 2, 7, 4. Then it will give you the correct value, which is 7, 7. 2. So it means after 100 days, we know that the chicken that will be infected with the virus has 772 chickens. Okay. So this is the growth, the logistic growth. So if we find that this is the number of chickens that we have, that is why I would say, okay, it will grow, but at some point there is a limit. Okay, I think I've deleted. I'll just put it somewhere here. So we are saying this is logistics. So you find somewhere here, that's where we have all our 772 chickens. So it means we started here with 1 chicken. So it went up somewhere here to how many chickens? 4 chickens. So this is the number of chickens that we had, 772. So it means it will grow and grow and grow and keep on infecting our chicken up to here where there's a limit. Now we don't have any chickens anymore. So it means it won't go, it won't grow further than this. So it can only grow up to this limit. So that's your logistic growth and your unlimited limited growth. Thank you. And now we can stop our recording.